for us.
Question, yes.
Yeah. Since we're going to discuss band unification, can you talk a bit about the electron-wave phase transition?
I could, I don't know, today. We could meet again if you guys are interested. It's a sort of orthogonal subject to grand unification, what we are discussing at the moment. But if there is interest, if it's not just Julian, okay, the best thing would be you guys talk to each other, we could meet. Well, I think the best would be to meet after the exam.
After the exams.
We can meet at any point, okay, you know, even later in June, if you're interested. I could give you a few lectures.
Are you going to be here in June?
Well, I'm supposed to go to a conference to the States. So we could still find the dates, okay, that we could even meet, you know, while you're doing a take-home exam, we can come and meet one afternoon. It's good to have a break. You can't just, okay, that remember, it will not be bad to take a little break, you know, pause and rest. So now I however, do want to go in this direction, okay? You see, today, what I wanted to do, what I was doing recently when I discussed the standard model, we need to come out of this with some sense of the avenue for beyond the standard model. Of course, other people will give you their avenues, and I want to give you mine because that's what I should do as a teacher of the standard model course. So in other words, to see where there could be an issue that we have to attack, and one obvious was neutrino mass, right? That was the best, I would argue, because the standard model predicted zero mass, and therefore we have to go beyond. There was an interesting potential direction, right? The fact that there is this strange strong CP phase, and it should be extremely small, could fit nicely with the existence of a new Goldstone boson, which, however, points to a huge scale. Well, there is one class of theories, all of them, with spectacular predictions, that have inherent large scales. That's the theories of grand unification, okay? So this is what I want to do, where the scale is even bigger than this. This is just a lower limit. And remember what he said, why I expected a large scale without giving any, you know, without further ado, I can say it immediately. Such series, because by this grain design, they want to unify quarks and leptons. They will create new interactions with transformed quarks and leptons, or baryons into leptons, and therefore we will get proton decay. And we immediately figure out there had to be a huge scale, right? So let's see how you already get some hints from me how this could be done. You even know, some of you, well, I think at the end it was only Julian who did SU5, correct me if I'm wrong. The others didn't do it, okay? If you do that homework problem, you would know how to break that symmetry, you know, you would have a complete glimpse into the symmetry breaking of grand unification in general. But what is this grand unification? Well, the standard model is based now, we did even some justice to the color, SU3 strong interaction, SU3, okay, we finally learned something about it, times SU2, and times U1. But let me not even mention U1 at the moment. You and I know that there is SU3 plus SU2. Remember when I started out the course, I said, wouldn't it be beautiful if SU2 would unify weak and electromagnetic? It would be really beautiful because first you have one gauge group, that's great, one coupling. So the weak coupling becomes equal to, in this, for example, theory, G would be equal to E. There's just one coupling. Then the only difference would be the gauge masses. And not only that, the charge would be T3. And therefore, being traceless, I would get charge quantization. A miracle in nature, okay. So we loved it. And we were reluctant, we finally did what Glesher did, we added U1, and it was painful. We lost all the beauty of the original desire. No unification, we needed to introduce an arbitrary parameter, the ratio of the two couplings. And more awful, we lost that quantization, okay. But there is at least today, you know, we could cry over that, but we know there is at least SU3 and SU2. Now I want to do what Schwinger wanted to do originally. So if I want to unify these guys, what is the minimal group? SU5. You can't do it in SU4. There are enough generators in SU4. But these guys are orthogonal. Remember, they have nothing to do with each other. You can't put part of this in SU4. You can't do that. Okay, strong interactions are orthogonal to weak interactions. Weak take proton into neutron or up to down. Strong keep down, down. Just change its color. So the minimal theory is SU5. What is the rank of SU5? 4, which is 2 plus 1 plus 1. Therefore, I get automatically 1. So we lost nothing. This, you could argue in the beginning, was a beautiful example of an ugly, of this tragedy of the ugly facts of nature killing beautiful theories. But since there is SU3, when I want to unify it, I get U1 for free. So what would be the advantages of taking this series? Number one, I have one and the same coupling. G3 equal G2 equal G1. They must be the same in such a theory. Of course, when I say that they are the same at some scale, right? Couplings depend on the scale. They're not going to stay, they run differently. So when you say that something is equal, this is very important. There will always be a fixed energy, and never again. Or maybe afterwards, yes, but not before. We'll illustrate that. At least at some energy, which I could call lambda unification. The scale of where the symmetry is actually broken, right? The relevant scale for electron physics is where I break SU2, that's MW. The relevant scale will be that some UMX lambda unification where new physics appears. But the couplings will be the same, and it's kind of nice. You see, now I can ask the question, if you wish, why is alpha alpha? Okay, which sounded crazy before. Well, of course, it's still crazy. But you can say, you can say, if alpha 3 is strong, why is alpha electromagnetic weak? Now that can be asked. Because if they start the same, then I can compute the difference. It becomes a meaningful question in this context. Previously, simply I couldn't address it even. These interactions had nothing to do with each other. But now they talk to each other, somewhere there. So I can correlate, if you wish, I can hope. For example, I can, another question is, what is this parameter? Can I predict it? Ratio of electromagnetic weak. Some kind of relation between the couplings I can look for, okay? We'll try to think a little more, okay? This is an immediate advantage of this approach. We'll go on. I get charge quantization automatically. Why? Well, because the charge, electromagnetic charge, must be the sum of the generators. We said that more than once of this original group. Whatever it is, I don't care. All I know that it's unitary. So I know that the traces of TA are 0. Therefore, trace of Q is 0.
Yes.
Therefore, charges are related, and we commented on this before. We'll now do it more carefully. Okay. And this, of course, I can't show you. There is an extraordinary work by Polyakov and Hoff who show that if charge is quantized, then there must exist magnetic monopole. I don't know if you appreciate the beauty or the importance of what we to find magnetic monopole, right? Centuries later. The things that you're told that cannot exist, right? The first thing you have to teach the child that you can't break the magnet, okay? So magnetic monopole. Another thing that we said, proton will have to decay. That's a spectacular process. Why is it so spectacular? Because it was never seen. It was looked for decades and decades, and the lifetime gets getting bigger. It's crazily big. So to see that, you know, whatever you look for a long time becomes important. Proton decay. So I hope I convince you that it's worth studying. So the minimum theory is SU5. Let's try to build it. And we already did the first step the other day. We said, well, we'll try the 5-dimensional representation. You know, when I did SU2, I tried the 2-dimensional representation. We take a geodesics approach. Please, we try to go simple. And we found out that, I think you got that immediately, right? The upper three components, let this be SU3 color. And these two SU2V, which is left-handed. So we said I could put here neutrino and electron. Then this becomes left-handed, you agree? Mm-hmm. They are left-handed, so this is left-handed. All 5 of them have to be left-handed. Mm-hmm. You can't change chirality inside the representation, you would break Lorentz symmetry. In other words, the symmetry here is SU5 times Lorentz. Then I have 3 quarks here. And the charge is, see how charge is nicely predicted? This is 0, this is -1. So this guy has to have charge 1/3. It's not arbitrary anymore. Okay, the miracle that the charge is integer product, the charge of leptons is integer of the quark, immediately gets answered. This has to be 1/3. And what is 1/3? It's an anti-down quark. So this is DC, DC, DC. Red, yellow, blue. Let me not write the index. This by convention is called, this is a fermionic representation I will also return. And it's taking as anti-phi. A convention. You call it phi or anti-phi. What I call a doublet, it's up to me. Okay, in other words, if I want a 5-dimensional representation, let me write it here, I need space. If I ask you, this will be an anti-representation, so for example, it would not be, this would be the tilde of this, so it would be EC. And remember there was a sign because of sigma 2, yes. Nu C. And then of course this will be right-handed. All I have to remember that ECR is CEL bar transpose. And I keep emphasizing that I can work with this left-handed guy or its complex conjugate. After all, this is just I gamma 2 DL star. Simply a complex conjugate. And therefore, this is now +1, so this would be a charge -3. So let's use that convention, down quark, to call this phi. First step done. Now that's not all, I have to place other fermions. So what can I do? I can try adding 5s, but that won't work because the beauty of group theory of simple non-abelian groups that everything is quantized and decided, so every 5 has the same charges. There's no U1 to play with. But where should I find the up quark? Where should I put it? What should I do with it? So obviously there must be a bigger representation than 5. So what's bigger than 5? Well, 6 is bigger than 5, you can tell me, 7, but I need a better number. How do you build representations of groups? You take the fundamental and then what we did in SU2, symmetrize or anti-symmetrize. You build everything like that. When we symmetrize spin half, we get spin 1. When we anti-symmetrize, we get spin 0. So I take 5, I have to do 5 times 5. What is 5 times 5? Well, that's 25, you can tell me. True. This is 25, but it can be symmetric.
Yes.
So there is
One.
symmetric plus anti-symmetric. How many, can you count one of the two, help me?
10.
One is 10, yes.
10 and 10.
10. And the other is 25 minus 10.
No.
Yeah.
Means,
If one is 10, the other is 15.
yes, but antisymmetric is
10.
singlet. There should be a singlet as well.
No. That's only in SU2. How would you build a singlet? Imagine. It's a miracle. How did I get a singlet? Because there were two indices. When I took the doublet, and I wrote I sigma 2, another doublet, right? U1, U2, let's say two doublet. Transpose. What this is is U1 transpose epsilon U2. So it's like writing epsilon ij, ui, uj. So you see, if I have two objects, then I can get a singlet when I anti-symmetrize. But if I want to do SU3, I have to take three objects. Remember when you do it in SU3, when you take triplets, you won't get a singlet.
Yes.
Fortunately. Otherwise, where would be these particles? You know, the visible particles we have, we proclaim must be colored singlets. And therefore, I immediately answer the question why there are no Carl singlets, QQ mesons. Then I have to take QQ bar, that's different. So this is 15 symmetric. Well,
I don't see it immediately why it's 10 plus 15.
can you see?
I can't see it. Why it's 10 and 15.
Well, anti-symmetric, remember, how would you do anti-symmetric? It's 5 times 4 over 2. Let's construct it. If you don't see it, why don't we try to write it? Write the number of anti-symmetric components. This is when we looked for the, you know, the joint of the orthogonal groups. This is an anti-symmetric thing, and it was,
Oh, yes.
you knew that, okay, it was 5 times 4 over 10. It's anti-symmetric, so it has to be 0 on the diagonal.
Yes, yes.
Okay, and it's 5 times 5,
Yes, I got it now.
and it's going to be 10 if you do that. So let's look. What can we do? What we are missing? Let's count. Which other states I should include? Help me. Which other? I'm doing one generation, of course. Then I go to the Xerox machine and I copy the. Well, these days we scan. You know, we don't Xerox. I'm sorry, the language is terrible. You take a photo with your iPhone, right, or scan it. You know? You don't even have to go to any machine. So what am I missing? I'm missing an up quark. Thank you. An anti-up quark. Or UL, you right? Let's call everything left. Okay. I'm gonna keep this left-handed fermion. What else do I miss? I have down quark, I have EC. I need an electron. No, I have an electron. I need EC, left-handed. Thank you. What else? I have DC, so I need D. So this is the minimum I need.
Left-handed?
Yes. Right. I wrote 5 just for us to have the quantum numbers, okay? But I'm going to work with left. So 3, 6, 9, 10. Let me try. Let's try. So these first 3 would be SU3. And then if you manage it, we go a bar and get a drink, okay? I invite you, if you have. But you have to construct it with me. I don't want you sleeping here. I know you may be tired. So am I. So, what is the, let's look at this thing here. How many states do I have here? Remember it's anti-symmetric, so I have 1 here, 1 here, 1 here. Anti-symmetric, there will be minus sign, so I have 3 only. Okay, there are always 3 when I come to quarks, so this is good. Now, what will be the charge? They will all have the same charge, you agree? Okay, this is an art of construction, so please pay attention, okay? You don't have to know that much, okay? 5, 10, this is 10. 10 is 5 times 5. Here is 5. These are the charges of 5. The first 3 guys have charge minus a third. So these guys must have the charge, I'm just taking it twice, minus 2/3. I'm multiplying this by this, thinking anti-symmetric combination, that's going to add up. Minus a third times a minus a third. So here I have to put a particle whose charge is minus 2/3, and it's a color singlet, it's a color triplet, there's no weak interactions. I look here, no,
Is that
no.
U and C?
This guy is a doublet.
Yes.
This is a doublet. Here, this guy is a singlet.
Yes.
Why? Because UCL is CUR bar transpose. This guy has no weak interactions, only strong interaction. Then I can't say it now. I put this guy here. So this is 1, 2. I'm going to call this U3. Or UC, I can write like this, 3. 1, 3, UC2. 2, 3, UC1.
Was that color?
Yeah. Well, you could call it red, yellow, blue. I'm calling it now 1, 2, 3. Just to emphasize that there are 3 of them. So this would be minus UC3, minus UC1. And we could think of some conventions, whether we could put a minus sign somewhere and so on. Let's not worry about that minor detail. The charge is fitting, okay, so this is good. So far, so good. Now, look here. These guys will all have the same charge because they have the same color. Particles of the same color are the same particle. Now, what will that charge be? This is the place 1, 4. Right? First row, fourth column. 1, 4. I'm multiplying this by itself. And I'm taking 1 times 4. What's the charge of 1 times 4? Minus a third plus 1. 2/3. The charge is going to add up. 10 is 5 times 5.
Yes.
So you see, it's sort of as if you are building a thing to be together. The charge is going to be double. Okay, we can write that formula. After all, charge is just the phase transformation. So if this guy has e to the I alpha, the other guy has e to the 2I alpha. So I need to put a particle whose charge is 2/3. Do I have a candidate?
Yes.
Yes.
Dark quark.
U1, U2, U3.
Why are you putting the ups like not in the SU3, neither in the SU2 part? I mean, in the 1, 4.
These guys belong to the triplet of color. This is how color is acting in a 3 space. Color is the 3 space. Weak is the 2 space. There is also here SU2 acting between these 2 states. This direction is color. The guys with the same color is the same particle. The same color. The guy whose only change is the color is the same particle. I'm not changing in the SU2 direction, so this must be one and the same particle with different color.
So it's
A
like
color triplet, for sure, by
this
definition.
is color and this is.
This is weak, yes.
Okay.
2 is
Okay.
weak, 3 is... Please don't be shy. I mean, here, keep staring and keep asking. As stupid as the question may look, okay? If you catch it now, you'll know it forever.
Can you repeat again why that is 2/3? Actually 2/3.
This is element 1, 4. I'm taking 5 times 5. It's here. I'm looking at symmetric element 1, 4 at the moment. 1, 4, that means I take element 1 and element 4. Element 1 is here, B, has a charge minus a third. Element 4 is here, has a charge plus 1.
+1.
Plus 1 minus a third is 2/3.
Okay.
I'll try to give you a few tricks today that are very useful, okay, that you don't normally read off in the books. Normally it's done in a very sort of cumbersome. And then, of course, you can do the mathematics. I'll remind you how you would do that. But it's good to get an insight. You see, how would I put, if I had 1, 5, then I would say, and notice it's 1, 4, or 2, 4, or 3, 4 is the same, because 1, 2, and 3 is the same guy.
Yes.
I'll get the same result, obviously.
Yes.
I said it has to be by color. I don't have to be that smart.
Yes.
So 2, 4, minus a third plus 1.
This is the same.
3, 4, 1, 5. Let's now do 1, 5. Element. That means I'm going to take 1 and 5. 1 is minus a third, 5 is 0.
0.
So there's going to be a minus third guy. This is down core. It better be,
Yes.
because this is SU2. If this is up, this must be down.
Yes.
Oh, it's fitting beautifully. I don't know if you can imagine now, late night, Georgia and Glass show, getting, when you feel the goosebumps, they are there. The simple idea, just finally, it could work. D, well, of course it will be the same, because this guy have the same charge, and this will be the same. So it's 1, 2, 3. Now the last guy, if I goof now, we can't celebrate it. We got still a few more things to do. 4, 5. Okay, now I want to do 4, 5. That means 4 times 5. Element 4, 5. I go and look. 4 has plus 1, 5 has 0. Oh, that's great. I'm going to call this EC.
Yes.
Everything is left-handed, so yes, EC is the singlet that I was missing, because I had a doublet. By the way, either I work with this or with this, you choose. And you will see in different books people choose different things. Just the way we decided in the standard model, we could choose left or right, it was up to us. And so there'll be minus U1, minus U2, minus U3, minus D1, minus D2, minus D3. So this is the beginning of the excitement. From that point of view, you can imagine their excitement. The standard model was taking off. Strong indication that it was a good theory. The year is 1974. Notice now that we have the same prediction as the standard model had. This is it. I cannot add anything more. I put all the fermions. I have an immediate prediction. Neutrino is massless. There is no room for an eye-handy neutrino. And I can't write neutrino mass that violates the symmetries, of course, that violates in the standard model, okay. So they were very excited. This is the reason why people that were doing this were telling me, for example, that I was wasting my time because I was working on neutrino mass. I was working on a different theory at that time. You didn't know. So I want you to see from our modern point of view, today we wouldn't be so excited neutrino mass. You would have to worry immediately. I'll address that later. Let's not worry now. Let's go back then and see whether we can construct a realistic theory from that point of view. So I took care of fermions. Okay. Now the gauge bosons, let's have a look at the gauge bosons. Or maybe before we do that, that's already done for us. It's a covariant derivative. Let's look at the Higgs element. I need, of course, to break the, so first Higgs. So there is the thing when you construct a new theory, you have first to worry about matter. which is fermions, quarks and leptons, what the matter is made of. Check. The gauge bosons are decided once you specify the gauge group. How many gauge bosons do I have? 24. There are a lot of them. It looks ugly at this point, okay? This somehow you say, oh my God, 24 gauge bosons, how are you going to classify them, okay? You see, it's not that ugly. Gauge bosons taken care of, so the next thing I have to make sure when I'm building it is the Higgs. So I need to break this SU5 down to this, preserving the rank. We knew that, you know, immediately, it's got to be an adjoint, and that's why there was a homework problem. So the first step, I break SU5 down the standard model, which we write like this: 3 times 2 times 1, SU3 first. This is through the adjoint, which is, we call it sigma 24 dimensional Higgs. But then, of course, we have to break the standard model down to 3 times 1, SU3 cross U1, and that is done by the doublet of Higgs in the standard model. Now notice here where I have the doublet already. The ideal thing is to take the smallest representation possible. Well, 5 is interesting because it has a doublet. Look at it here, it has a doublet. Well, not only doublet. You're never going to get only that because now we have a big theory, but the doublet is here. So you won't be surprised that they start by trying the 5-dimensional Higgs for this step. And the 5-dimensional Higgs, look at it, the way it would look 5 plus, 5 0, with our conventions of quantum numbers, positive, neutral, and then I'm predicting the new scalar, which carries color. Funny guy. You have to figure out what it does, and I know what charge it is. So this is often called T1, T2 for triplet color. I don't know, there are different notations. Depends. This is a 5-dimensional Higgs. If I'm right, I need to be able to write Yukawa coupling. So if I work, let's, you know, most books use this. Most reviews, most papers, 5 and 10. There's a good reason to learn this and to read this notation, because we don't have neutrino here. So if I want to add a neutrino, then maybe I should have a more complete theory in which I would put these guys together. If I put them together, they should have the same chirality. You can't break Lorentz-Unit. So let's use everything left to get used to that. You will see the same reason when you write supersymmetric theories. They have to have the same chiralities, the states. You can't build a supersymmetric field theory. You have to get used to that. It's just a notation. Because when there is right, there is left. When there is left, there is right. So let's use that. So look, Yukawa. Let's try Yukawa coupling. 10 has 2 indices, right? What do I mean by 10? This is like having phi I, phi j, and then anti-symmetrize this. Just 2 indices, okay. So Yukawa, there will be 5 fermion bar. There will be 10 fermion. I will just write schematically. Okay, this has 2 indices. Let's write them as lower. The anti has an upper index, right? This is the convention, right?
10 is that.
This is 10. Thank you. Should have written. 10 fermion has 2 indices to account for this being a matrix. 5 is a vector, or column, you can try to write it. So I need to get an invariant thing. So I'm going to contract here, I and I. I'm getting there. I need to put the Higgs. So what should I put, phi or phi star? I'll put phi star. I have to contract this index. So I put phi star, which means that the index can be H. This is obviously invariant under SU5, and I can make it Lorentz invariant if I stick in the famous charge conjugation, because this guy is left-handed, this guy is left-handed, so I would put the charge conjugation. You see, inside there are, remember that this is always a field psi C, how to call it, psi left, sorry, when I have two fields, psi 1 and psi 2. All I have to is to put the charge conjugation. This is actually transpose, but let's not worry now about too many deaths. Crucial thing is charge conjugation. This is often omitted because people want to emphasize the group theory aspect of that. That's what you have to understand, which the Lorentz part you presumably understood. So I won't write. I just want to get the SU5 clear, and then we can try to be more explicit. So, okay, but it's not enough. I need two Yukawa couplings. Both up and down quarks curve. Actually, I need more because charged leptons. In general, I need at least 3 massive states. But,
what is the star?
Star, it's the phi bar. I don't write bar on scalars. Anti-representation.
Is the complex
There is always a doublet and anti-doublet. There is SU3 triplet and anti-triplet. So this is anti-5. On Fermions I put bar because
this just complex conjugate, right? Okay.
complex conjugate provides a
Why you want to the complex conjugate?
groups here.
Because you want a singlet here. I want quantum numbers to be 0, but can you explain it a bit?
When 5 became 5 is a fundamental representation of a group, then phi star is what we call the anti-representation of the group,
Yes.
phi bar. Now, how do I know that I have to put here? I have to think about, it's not this fancy language, it's actually answered here. I have to make this invariant.
Yeah.
If I'm on qubit invariance, I have to get rid of my indices. I have to contract. This must be, the indices might disappear, right? It's that elementary. Upper and lower provide the singlet, right? You've done that in SU3. You know that Q bar Q is a singlet. You always use that, you see? Not QQ, Q bar Q if it's SU3. And that means this is Q star, Q. One must be, bar is, bars because they're fermions, but all you have to remember that bar is a star.
It's because of the Lorentz, you want to make it similar to the Lorentz?
What? Here? No, I want to make it an SU5 singlet. I forgot the Lorentz group. Well, I keep in mind when it's a fermion, I put bar. That's the only thing that I remember. It's a notation, okay. In general, I will put a star.
Okay.
In fermions, we have a convention to put a bar because it's not enough. Lorentz group will not be, it's not enough to put the stars. You have to put the bar. They are spinners, so it's a little more involved. But from the group point of view, bar is star.
No, I understand.
There is some gamma zero, but
I understand that those are fermions and they have the bar. Because
right. All I mean, if there is a lower index, I can only contract it with an upper index. Lower index, I will contract with an upper index.
Yeah.
An upper index is a complex conjugate representation. That's a convention.
Upper index means.
Upper index it means the complex conjugate.
Okay. I didn't know.
So sorry, no, my fault because I assumed that you guys know that. But you had a group theory course.
No one, no.
It can't be.
We did that.
Okay, I know, no, but that's mentioned. Yeah. Okay.
I don't remember the convention for group theory.
I also didn't.
That ought to be the first thing in group theory. The rest,
He didn't
We
mention
actually,
it.
we actually did it this morning in the SOC course.
Yeah.
But on the SOC course today, not in the group theory.
Ah, he did that?
We did the
who taught you group theory?
Nine.
Oh, we did the complex quantum representation. It's like
He must have.
the index placement is the
Yes,
convention.
yes. I
Okay,
didn't know this.
maybe he was not explicit.
Yeah.
You see, he knows fancy group theory. I'm okay. I like people to know group theory in their fingers, I used to say. I'm much happier if you know, because you end up knowing, thinking diagrams and stuff like that, but then I push you down to write to me simple invariants, you will know this, okay? So it's all. So I apologize here, I assume that you know. So we write lower index for representation and the upper index for an entire representation. That's a comment. So there are two ways of getting invariance. One is lower upper index contracting. Really, this is not enough. Notice this is just one Yukawa coupling. By the way, notice that, look at the up fork. There is no up fork in 5 bar. So if I want my up fork to get a mass, it has to be all in 10. Up fork lives only here. Up fork is not going to get a mass from here when I give a wave to the 5 Higgs. It can't, it doesn't live there. So, you know, it lives inside, but it's not here, okay? And to get a mass, I have to take one guy from here and one guy from here. So this is not enough. This will give me the mass you can get to the down fork. I need one more coupling. Well, there is always another invariant in SU2. In SU2, by the way, actually you were used to that. You used to write invariants phi dagger phi. But what is that? That's phi star phi. Phi I star phi I. It was there. It was somehow maybe hidden to you, but it was there. That was the only way I wrote invariants phi dagger phi, which is upper and lower index because this is an anti-doublet, or epsilon ij phi I phi j. This is also an invariant. Where for scalar it vanishes. You need two different scalars. Remember, there is epsilon and j, so you can anti-symmetrize. Okay? If I want to do SU3, I would have to symmetrize 3 times.
Okay.
If I want to do SU4, I will symmetrize. If I want to do SU5, I'm going to have to symmetrize 5 times. There is actually additional coupling, which is epsilon I. Well, let's write it like this to be more fancy. Ln 10 fermion. Let's write JK, 10 fermion Ln, and then I can put the 5 Higgs here, which is I. What I did here, I contracted lower and upper indices, and I was forced to put phi star because I already with phi bar had to contract to one index, so then I could only contract another index. Now my other option is to take all 5 of them to be one and the same index, but then I have to anti-symmetrize. This transform is a determinant. Remember, you knew it in SU3. Each of these goes as U, 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 and this is simply the determinant. SU5 determinant to 1. So these are the famous invariants of SU group. In SUN group, you have to anti-symmetrize n time. And that's invariant. Right? All I'm saying is that. So let me summarize. If we always, our invariants, remember up to now, either look like Q bar Q, or L bar L, or phi dagger phi. They were group invariants when they could be the group invariant. So this is of the type phi star. This is of the type, let's say, representation, let's call it phi star phi. This would be invariant. Okay, in really what I mean that is phi dagger, because some representation fundamental goes into UF. So strictly speaking, I just write simply, this is phi dagger. I have to lie down, right? Because then phi dagger goes into phi dagger, U dagger, so that phi dagger phi goes into U dagger, sorry, phi dagger, U dagger, U phi. and this is phi dagger phi. So this is one type of invariance. It always star times the field. Okay, I'm isolating the. And the other is anti-symmetrizing, and anti-symmetrizing is saying that if you have epsilon ij to n index type n, you will have, how will I call it, psi I, psi j to index n. This transforms each of them as u, I prime, psi I prime, u, j, j prime, psi j prime, and so on. And these things gives you epsilon the prime times the determinant of u. This is what the determinant is. You can check it explicitly, please. But that you should.
Yeah.
The Rhine must have taught you. And this is, by the way, the only two Yukawas I can write. Convince yourself, what else can I do? So I have two Yukawas. This is interesting. I'm going to get some relation. Because they are up quark, down quarks, and electrons, or leptons. SU5 is going to predict immediately something, okay? Yes?
I don't understand why the first combination gives mass to the electron, I think, and the other one gives mass to the
Let's see.
ground core.
Let's see. Let's see. It's not that obvious. It's true what you said, but let's see that. So I hate to, this takes a lot of space, but I hate to erase it. Okay, look, I'm going to erase things like this. All I have to remember that 5 Higgs is like this guy. So the value is going to go here by my convention. It's okay? We accept that, okay? It's a convention of my choice of what I mean by doublet. So in other words, 5 Higgs VEV is 0, 0, 0, 0 V. So let's see what we get. So let's look at the mass. And then I will put the Yukawa coupling names later after I see who is getting the mass, okay? So this is 0, 0, 0, 0. So this is index number 5. So in other words, this is 5, okay? Let's remember, if you allow me, I'll just put 5, 8, 0, 5, and there is some V outside. If this is index 5, so I can contract here, and this is 5. Okay, when I contract here 5 in 10, did I do it correctly? Yes. I still have an index over, I don't have to worry about all 5 of them because it's anti-symmetric. 5, 5 doesn't exist. So what exists is, so how shall we, let's call that, let's call 1, 2, 3 alpha and 4, 5, 8. And 1, 2, 3, 4, 5, I call I, J, K. Okay? A, B, C is going to be SU2 index, alpha, beta, gamma, color index. Okay? So where am I? I have to look at the component, let's say alpha 5. Let's look at the color first. Here I am, alpha 5, so help me, 1, 2, 3, 5. 1, 2, 3, 5, that's down quark. 1, 2, 3, 5. That I would call, in other words, from here I'm going to get D alpha, alpha, okay, there will be a VEV, and then the same index here in the 5 bar, that's going to pick up DC. Good. I was going to look at the wrong one. DC alpha. And this is what I wanted. I have charge conjugation to put aside because this is really the mass term for the down quark. There is D bar here. So I got the down quark. So I'm going to call this Yukawa coupling. Yukawa D. I don't know why I put the VEV That was 505. Wave should go here. So I go to gamma D. Notice an interesting thing. I can also have an index 4 here. You still with me? 4, 5 is EC. Okay, so I get plus EC, the same wave, the same Yukawa. So why not you put wave outside? And if 4 is EC, I have to look here at 4. Something is wrong. Why am I wrong? You see, one has to be careful here, because we need an invariant. You see how it happens, okay, that this notation may be a little misleading. You know, there is nothing, I'm not being careful here about notation, whether it's dagger or star, whatever it is. We have to have an invariant in the SU2 space. But to have an invariant in SU2 space, I need I sigma 2. This is, I took a doublet. You see, I took a doublet here.
Yes.
And I took a doublet in this guy, okay? I think both times I took a doublet. There is actually I sigma 2 hidden here that I have, okay? Maybe I'll give you a little, at some point, let's just accept it here, how I would write it in a smarter way to be sure that I get it right, okay? You see, I didn't even have to do this calculation, okay? I'm making the prediction that electron and down quark should get the same mass. Now notice that this prediction I get without even giving any thought to it. When I break SU5 symmetry, SU5 was broken by the adjoint, but the adjoint doesn't couple to fermions. It's a 24-dimensional Higgs, it's never going to couple to them in this matrix. We know that. Because that's the Higgs that is basically the singlet of the standard model. This is the Higgs that breaks SU5, okay? In order to give fermion masses, I have to. Now this breaks SU5 to SU4. SU4 remains. So when SU4 remains, we have to look here. This is the original representation 5. I have to look here to see what is happening. This is the better way to think about it. And this tells you that these guys are in the same SU4 representation. There is no difference between the down quark and the electron, as far as the Higgs is concerned. You and I know that there is a difference. One has a color, the other doesn't. But the Higgs doesn't know that.
So the masses.
The guy doesn't see that. The guy still keeps SU4 symmetry. So this can be understood immediately. These guys have the same mass, okay? This is an interesting prediction. And people try to argue that this could, you know, both are, if you look at the electrons, it could even hope to work. It's true that these guys lighter than the down quark. It's true. But this is the prediction, not that everything runs, everything changes with scale, not just couplings, masses, everything runs in field theory. All the parameters of the underlying Lagrange. So when this happens, this is at some scale. When SU5 is a good symmetry, you could then run it down. It was not completely crazy. It doesn't work. You see, you can know immediately. It won't work for all 3 generations. The ratio for generations are different. Just to remind you, an electron is 0.5 MeV, and down is roughly some number around 5 MeV. The ratio is about factor of 10. Then second generation M-muon is 100 MeV. You can see the failure immediately. M strange is roughly 100 MeV. Completely different. So if it works here, it won't work here. You know, at the end, it won't work. Okay, we can think what could correct it. And then if I look at the third generation, M tau is roughly 2 GeV, and then bottom is roughly 4.5 GeV. So each generation has its own ratio, okay? So this would need some correction, okay? This is the first sort of strain that the minimum SU5 is bound to have problems. And there could be some things, or maybe thinking of loops, or maybe thinking of higher dimensional operators, as we call them. There were ways, smart people find smart tricks, okay, but there is a hint that this could fail us. Now here, we could easily find out that the up core gets a mass. Let's see. This will be 5. In order to pick up a wave, I would choose 5. So this is 5, so this is 5. If this is 5, then I have 1, 2, and say 3 and 4. So I go in 1, 2, that's UC. I go into the 3 and 4, it's here. U3, look, I get a mass for the up core. Immediately. That's okay. Of course, I get more prediction, okay, the same thing as in the standard model, it has its own Yukawa coupling, but it works. So if you and I decide to ignore this for the time being, and let's do, and for the time being, at least for 15 minutes, we can, I can make more comments, but let's pretend that it works. Then, if you think you got this picture, then we should talk about the gauge bosons, because that's where the interesting, that's where the drama lies. The new interactions, okay? We have to understand what the new, this is bookkeeping at the moment, they may look beautiful, but so what, you can say. Unless there is no new physics associated with this, what I'm doing. This is just, song and dance. Fancy group theory exercise. When you have to do the Higgs physics, you won't easily fail because you have freedom. Think about that. If this Higgs doesn't work, you'll take another Higgs and so on. Okay, nobody knows in advance what Higgs should be taken. Okay. Well, it has to have a doublet, but it may be some other representation if this didn't work. Okay, so there can be some hope that you will sort of fix your problems. But if the gauge bosons, there is nothing you can do. You told me what your group is. And then let's just go on and don't be lazy, do the calculation and see what happens. That's fixed by the covariant derivative. So let's try to see how we would classify the gauge bosons. Now, what is the gauge boson representation?
The joint.
It's the adjoint. And you remember what the adjoint is? Let's just remind ourselves, it is U, A, U dagger. A for adjoint, or sigma as I wrote it, okay. Why? How do I know it's U, U dagger? Remember, because it comes from here. So inside here, there is Q bar, A, let's call it this A. So when I write A, I mean this, with some fields Ti. Remember, we expanded the generator. Obviously, this will transform correctly because this goes, Q bar goes into U dagger. Bar is just a Lorentzian, U, A, U dagger, U Q. So we know that. In other words, gauge boson is the, you see there is another word, of course, of doing another way. One is symmetrize. You can anti-symmetrize, or you take anti-fundamental times fundamental. As we used to do with SU2, we would write phi dagger phi in SU2. Anti times. That, of course, is always there. And in particular, gauge bosons always do that, okay? There is no freedom with gauge bosons. This is good. So this is 5 times 5 bar representation, we call it. So we have 24 gauge bosons. So it's again 5 times 5 matrix. Let me make enough space. So let me try to create as much space as possible. The analog of. So there is 3 times 2. So here is the part which has only color. how many will there be? They're called gluons. That I knew that had to exist, okay? In the 24 representation of gauge bosons, which is a 5 times 5 Hermitian traceless matrix, okay? So in other words, trace of A is 0, A dagger is A. This is the reason I write A is PA, phi A, summed over indices. So here I have my 8 gluons. Good. What do I have here? The V guys. W and Z. But actually there are 4 of them. But remember this is traceless, the rank is 4. So along the diagonal, in other words, it's not just 8 gluons. There is someone living on the diagonal. Well, you know that photon lives everywhere. It doesn't live only here, photon. You see, SU2 lives here, but the photon lives everywhere. There's a U1 guy that lives everywhere because this guy carries charge and this guy carries charge. So here along the diagonal, and here there is W plus, W minus, Z and gamma. Okay, 4 plus 8 is 12. This is the standard model situation. There are 12 gauge bosons, 8 gluons, 3 W's, WZ, and 1 photon. So I have 12 more.
One question. The photon lives on the trace. I mean, W, the 2 W's and the Z live in the SU2. And the
Photon is going to live everywhere because here, you see the guys that live here, they carry charge in the SU3 space. So the photon.
The 4 live everywhere?
No, the weak part live here.
Okay.
They don't carry color. Well, the guy on the diagonal, of course, doesn't carry color. Okay, just to say, really the best language is, okay, let me be precise then. It's not really W, since you really pin me down. This is before symmetry breaking. You define your state before symmetry breaking. And then there is A1, A2, A3 of SU2. And there is B. Well, B lives. What I meant to say, here SU2 lives. SU2 is in the space of flavor, nothing to do with color. But the B guy lives everywhere.
Okay.
But if it lives everywhere, why does it take an extra position?
I can put it, I don't know how to.
I mean,
Lives everywhere.
it has 3, we have here 3.
Sorry?
This part of the matrix is 3 by 3, right?
This is 3 times 3 gluons. This is 2 times 2.
Okay.
This is weak part.
Yes.
Oh, I didn't draw it maybe. So this is 2 times 2 here. Right? Color is here. Always. And this is 2. This is 2. This is 3 times 3. This is 3 times 2. No, I have in other words 12 more gauge bosons. But notice that I don't know how to call them, so these are some unknowns. So I call this X. Notice that this must be the same guy because color is a good symmetry. So I should call this red, yellow, blue, or 1, 2, 3. Let's be serious, okay? There is no red, yellow, and blue. This is just to impress the girls, okay? Here we have only men, so you can say this is just to impress the girls. That we work on series of color and charm and whatnot, okay? But this is just a boring SU3 index, to be honest. You know, it was good, you know, it helped a lot for the field. You know, Gelman did a great thing with this, with the names. Not only Gelman, but most. And then, okay, there is another guy here. Must be the same guy because he has his color. Notice that this guy belonged to the SU2 doublet. So in a sense, it's like one new particle if you think of that. All you have to remember that there is it carries the SU3 and SU2 index. It's a doublet, but it's a very strange gauge boson, never seen before. It's a colorful gauge boson, flavorful. It's a funny guy. And that's all you have to remember, because this is, remember, this is Hermitian. So if that's X, this is star.
Yes.
Or you can call it dagger or whatever. Epsilon 1, Y1, Y2, Y3. So there is not much to learn. It's not so hard to study. I have one more interaction. And if I'm smart, if I write it in the SU3 invariant and SU2 invariant form, I'll just have one, basically. Okay, but I break it down into components, I'll have two. You and I never write color, okay, it's boring. We don't care, we sum the color index, right? We want to see what happens. So although it looked sort of, 12 new gauge bosons, it's basically one doublet of particles. What is the charge of these guys? Let's count charges. Now it's 5 bar times 5. So for example, if I take 5 bar times 5, then I take, for example, look, in the gluon space, 5 bar times 5 will add up to 0. 3 times, and so on. And for example, look at this, I will have ECDC. Look at the funny guy. If I take one of the guys from here and one from here, right? 5 bar times 5, I'll have a guy who has charge I4, 1/4, 4/3. Never seen before. You have a fractional charge gauge, which is predicted. What to do? So this guy has a charge 4/3. Can you tell me what is the charge of this guy without looking anywhere? Don't look there. Look at me. It's a doublet. What is the difference of charges in a doublet? One. This guy has 1/3. Well, you could say it could have been 7/3. Okay. It was not enough to look at. Yeah, I'm sorry. But I had to get to 7/3. It's sort of. And 1/3, for example, I get 4 times 5. Sorry. This is index 1/5. So it's a third, or minus a third. Of course, if it's a third here, it's a minus a third here, and vice versa. It doesn't matter if I make a small, I should be careful. Maybe this is minus 4/3, but then this will be 4/3. Both of them are there. If there is W, there is W star. If there is W plus, there is W minus. If there is electron, there is positron. Okay. So that.
One question.
Yes.
You're making this 24A is the symmetric part of 5 bar 5.
Sorry, this? Not symmetric, you don't symmetrize. No, 5 by 5, you take
5 bar
traceless.
5 bar 5.
Yeah, you don't symmetrize. You can symmetrize the same representation, but you cannot symmetrize opposite.
Okay.
5 bar times 5, one is upper, one is lower index. That you cannot
When
symmetrize.
you're comparing 5 bar by
No, this is
5.
just before. This is traceless Hermitian, but not symmetric or anti-symmetric. No, it's made out of 5 times 5 bar. This is what a joint is. A joint is coupled like Q bar, AQ, 5 bar times 5. And joint is always that. Gauge bosons are always that. Anti times the representation.
Okay.
It's look at here. That's how they couple. They couple to 5 bar times 5.
Okay.
So I can read off contour numbers now taking 5 times 5. This time I have to look at 5 bar times 5 bar.
Okay.
Important. Please let's make sure what Jorge is asking. This should be clear to everyone. I may rush here. When you be doing these sort of things, they look easier than they are. Now I don't have much space, and I'm trying to make it visible. if I have a boson, no, what I should do? Now I should compute the covariant derivative, okay, but not at 3:15, second lecture, that we are not going to do, okay? You could make it as a take home. I mean, in a sense, you don't have to learn that, but you could do this thing, you could just take the, okay, maybe a little, but let's think about it without doing a calculation. This guy has a charge 4/3.
Shouldn't be minus 4/3?
Sorry?
Shouldn't be minus 4/3?
Yeah, of course. If there is 4/3, this guy will have minus 4/3. So they're both of them. When I take 5 times 5 bar, look, DC times EC is 4/3. Bar D times E, well, here there is sigma 2. I should be careful. Or here, I always have to be careful. Then the charge will add up to it's a Hermitian matrix. So
Okay.
particle and antiparticle go together. And that's what this is why I'm arguing that actually there are not that many gauge bosons. The situation is not that bad. So I have a guy X which gets charged 4/3. So how could it couple? Let's just think. Let's not do any of that complicated algebra. Let's just think you and I. And he has to take a left-handed fermion to a left-handed fermion. The same representation, for example, it comes from 10 bar D/10, 5 bar D/5. So let's look at 10, for example. What could I get from 10? That this adds up to 4/3. Well, when I take UC bar, UC bar, I can put gamma mu, okay, if you wish. Right? Because this has charge 2/3. This has charge minus 2/3 bar makes it 2/3. So this should be this guy star, which I call minus 4/3. See, that a very interesting interaction that up quark can become an anti-up quark. What else? Can I get any other way 4/3 here? I guess. Look. D bar. Well, let's check. I should do the calculation, but I'm lazy. D bar is C. I could get that. Let's check I should get the right charge. Now it's now fixed by the first term. So the charge of this is +1, and this is +1/3. That's okay? So this will also be there. More or less, if it can be there, it's going to be there.
Yeah.
You can do explicit calculation, okay, but that's going to come from, let's see what could come up from here. Could anything come up from here? Yeah, sure. If I can have D becomes DC, I can have E become DC, or vice versa. Let's get the charges right, so it should be +4/3. Therefore, I may get EL gamma mu DCL. And maybe there is some coefficient here. You and I don't care about precise coefficients. All we want to see what happens. But what we are learning. Okay, this is essential.
One question.
Yes, please.
But there is not any, like, in this model there is not any extra neutrino, nothing. Just standard model, plain standard model.
This is just a standard model. We have just managed to unify standard model. We are not predicting any
So
new.
you are unifying standard model, but not predicting any.
No new fermions. We are predicting new interactions of the same standard
No,
model
yes.
fermions.
Yes, but
That's a prediction. This is what the beauty of doing physics seriously. Instead of building models, you say, I'm going to take. This is the real way of doing it. I like when unification. I take the minimal theory and see what happens.
can you give mass to the neutrino in this model?
No.
No.
That's why you're saying. there are good theories that give mass to the neutrino.
Yeah, sure. I'll talk about it in a second.
Okay.
I would have to extend this theory if I there is somehow SU5. You know, it's supposed to be grand unified theory, but then I have one fermion in 5 bar, one in 10. There is something. It's a nice theory. We should be able to put it together, the fermions. That would be much nicer. So we can go on and cure whatever problem there is, but you know, maybe we should also respect this beautiful prediction which failed and build a different theory, okay? I'll comment about that in a moment. Let's finish here. You see what happened now. Why actually there is proton decay? Because I said what I said was not correct. I said we will put quarks and leptons together, and therefore quark becomes a lepton. But that by itself does not violate baryon number. If quark becomes a lepton always, I still may preserve a baryon number. Imagine an interaction like this, without this. Can you do me a favor? Try not to see this. Quark becomes a lepton. Imagine just this piece. Then I would say that this guy has a baryon number minus 1/3, or whatever. Yeah, minus 1/3. That could be okay, but what is happening here? Why? I could just look at this and know that there is baryon number violation. I put quark and leptons together, but also anti-quarks. Now there is no any more of preserving a quark number, okay? I put quark and anti-quark together. Remember, it's like Majorana neutrino. Majorana neutrino is both particle and anti-particle. That's going to violate that particular thing we call lepton number. Here, this has to violate a baryon number symmetry, okay? By its very definition, that's the beauty of grand unification. It's not the theory you're inventing to account for that. By the very fact that you want to unify, you predict baryon number violation. And here it is. So let's draw it. Let me keep only 5 fermions here. So let's draw it. What I have an up quark becoming, so up quark enters. Let's do like this, and becomes, no, maybe I start with here. Up quark enters and becomes UC. Here it is. Okay. Then I have an interaction in which, well, if I have this, I have also an interaction plus X, which is ECL bar. Gamma mu DL, for example. Let me write just one. So D enters. And how do I get this? By the way, I forgot to do that. There I emit when U enters, and this guy's X star means X is going up. Okay? X is going up. X is going up. Here it is. X enters. D enters. And EC comes out. And this guy is watching. You can imagine how amazed this guy is, you know, what's going to happen, worried what's going to happen to me, but you can't help it, you know, it's like when there is drama. Drama tends to be irresistible. What we have, this is called a proton, becomes a positron, and this is called a pi 0. We just predicted proton to decay. And it's given by effective interaction, which is exchange of the X boson. So whereas the light time of muon goes as GF squared mu to the 5th, please don't ask me to write factors, which is mu to the 5th over mw to the 4. There are all kinds of 192, I don't care. By the analogy tau, no, this is not tau proton, this is gamma. Gamma proton would be m proton to the fifth, mx to the fourth. And therefore, lifetime of the proton, it's the other way around. It's mx to the fourth over mw to the fourth, m mu to the fifth over m proton to the fifth, tau mu1. I can predict proton lifetime now, if I know mx. Sorry. George I. Glashow didn't know mx. So what they did, they wrote this down, and then they, at that time, this was bigger than about 10 to the 30 years. And you get the limit on mx. And of course, it has to be huge. I remember at the seminar that, I'll never forget that, because I was just starting out my research. 1974, I go to the seminar to Columbia. There is this fellow Georgia giving a seminar. The title of the seminar, would anybody in her or his mind say that proton is unstable? He's talking about this all the time, and you know, he then writes this formula, and he concludes that mx, we can put the number, is about 10 to the 15 GeV. Once we did that, actually, you can put the numbers, you know, tau mu. So he called them, he didn't call it, this would be some kind of intermediate vector boson. He called it intermediate vector baseball. Okay, you know how heavy it is, it's crazy to talk about it. I was sitting in the third row, and the row in front of me, there was T.D. Lee, Al Mueller, a well-known theoretician, and there was old Rabi. Maybe I mentioned this. A great physicist, Nobel Prize winner. He's shaking his head all the time, and I can see that he's very unhappy all the time. Just what in the world is bugging him, you know? So after the seminar, we are standing there accidentally, you know, with a bunch of other friends, graduate students. He turns out to T.D. Lee and says, "What proton is he talking about?" And you can see, you know, T.D. Lee, who likes to lecture, wants to give him a lecture. And then Al Mueller, with a dry sense of humor, you know, nucleus, proton, and neutron. And this guy, you should have seen the look on his face. But it says, but he's crazy. Everybody knows that proton is stable. Again, T.D. Lee wants to explain to him, why would you know that proton is stable? You see how strong the prejudices are. This was a great physicist. Al Mueller says, well, George I doesn't know. And so this guy walks out, and he was very sad and embittered. Apparently, the brightest new star on the horizon doesn't know what everybody should know, that proton is stable. This, I told you, this prejudice, because they didn't say proton decay, they assumed barrier number conservation. And then if you assume that, then proton cannot decay. Now, this is what a good theory should do. Okay, this is sort of a lesson I want to make through this job. Instead of postulating ad hoc global conservation law, your theory, if it's good, should calculate departure from that law. But in order to be good, I have to calculate mx, otherwise, this is just words. And 6 months later, George E. Quinn and Weinberg, I had mentioned this before, they say, we know what mx is. That's a scale where the coupling should unify. They say, you guys claim, it was the same Georgia, so he couldn't say you guys claim. Well, I claim, it was interesting because he was a bit sad. He says, you know, how can I take this serious? The scale has to be very large. That's why he put the title. And you know, that day I remember we were sort of, it looked all beautiful, but then, okay, well, some huge scales that you'll never even think how to predict. Okay, if the theory is good, then I should do the run. I check the coupling constants. They took the numbers of those coupling constants. Alpha 3 goes like this. Alpha 2 goes like this. Remember, alpha 1 is not asymptotically free. There are no gauge bosons there. It grows. Right? B. To be positive, you need Young Mills. So they got this. Roughly 10 to the 15 GeV. And you can imagine why many people, including myself, found this so exciting that majority, or at least surely young people entering the field, then turned into this, and the whole world rushed underground, as Goldhaber used to say. People started to look for proton decay everywhere. And the best guys are Super Kamiokande, right? The irony of looking for proton decay, they found neutrino oscillations. They also set a great limit. The proton lifetime going to, especially the mode that was very interesting, pi 0 E plus, is now close to 10 to the 35 years. But let's say, surely bigger than this is established. And that's a blow to. Of course, when you do this calculation and you want to get a precise number, there will be details of the theory that you don't know very well. So this is not a blow to grand unification itself. So that doesn't mean that it's ruled out. What people learned, look, SU5 had problems. I predict this strange relation between down quark and electron mass. I predict neutrinos massless. I actually even predict this if I take it seriously. When people measured couplings better, this guy went here. There is no unification. And if there is no unification, you cannot talk about imagining SU5 gauge group. They must be, at that scale, they must be the same. You see, the beauty of new physics, and you can do that. I could show you. If we were to meet again, I could show you. Then they run the same. When you hit the threshold, if they unify, they will run the same way, because the new X, Y bosons, they change. Remember, you start running when energy is bigger than, when you are lighter than the energy. So you start running here X and Y, and they make them run equal. Okay, this is very nice. Maybe we can do that. Would you like to do that in 2 or 3 minutes?
Yes.
I mean, it's nice to see, instead of using words, okay? There was a lot of words. Let's see if you and I can compute that. If you fail, forget it. We stop. I don't get it right. So Bn is what? What was that? 11/3? And minus, no, what was this? 2/3 df minus 1/3 d scalar. Okay, so B3 is, this is 3. 33. Remember I computed this? This was 1 for up and down quark. We got 2 end flavors, right? Over 3. B2, 22 thirds minus, okay, how does it look? UD and UE. These are the doublets. So if I look at the one generation, okay, why don't I write this minus 4 number of generations. We are now, I can safely talk about generations. I'm running up there, high above you and Pavel is seeing. Now we are adventuring to go all the way to 10 to the 15. So what do I get here? I will get, what is T for the fermion? It's a half, it's a doublet. It's a half, but there are 3 of them. So I get 3 half plus a half plus generation. So I get the same coefficient, 4/3 number of generation. Minus 1/3, and the doublet, Higgs is a doublet, so this is what I get for B2. So let me just say, do B3 and B2. Okay, we don't have to do everything. We can do U1 at some other occasion. I want to just tell you one last thing. So, and of course they are different from each other. Notice a nice thing, that the difference between those guys, that they cancel the generations, okay? When I look at the difference. So the relative running, they don't contribute. There is an explanation for that, but okay. It's just amusing at the moment. Explanation requires some group theory thinking. Okay, so what is new? I have now, so this is how they run up to mx, this new scale, unification scale, the mass of the new gauge bosons, right? So now if I want to happen, what happens afterwards? So the B3, let's say, this is below, this is above, would be 33 minus 4 n generations over 3. Then I have to add x and y. No, I should write, this was not a smart way of writing. I should write TGB. Remember what T is? T delta AB is trace TATB. Okay. So X boson. They will be, this guy is going to run 11/3. But what is its key? Notice this is not the gluon, but it carries color. It's a triplet. It's a fundamental. Therefore, it's normalized to a half. Remember, T of the fundamental is a half.
Yes.
T for the fundamental representation. This is a convention. So there'll be a half here for X boson. But remember, there is a Y boson. Why there is a Y boson? SU2 symmetry.
Yes.
If there's X, there's got to be Y. Well, we found it. Plus 1/2. What else have we added? We have a 5-dimensional Higgs, which is, remember, the triplet here and the doublet here. So this guy is a triplet. So there will be minus a third times a half. Agree?
1/2.
This is a fundamental of SU3. So I put a half. You're still with me? B2. Well, I had 22 minus 4 n generations. I don't know why I wrote it the way I wrote it. Minus 1/3 times a half. Now, what am I adding? I'm adding a doublet of gauge bosons. So I'm adding 11/3 times a doublet of gauge bosons, which is a half. But they come in 3 colors. So I should multiply by 3. See, X and Y, these are triplet under color. So in the color space contributes a half. In the SU2 space, this is a doublet, contributes a half. But there are 3 of them from the SU2 point of view. There were 2 of them from the SU3 point of view. 2 of them from this SU3 point of view. And nothing new. This guy has no weak quantum number. It's a color triplet. So I stop here. So if this doesn't come out right, I'll be sad. Well, notice this is good. This is equal to this. Okay, if I'm right, they should become equal. Because if I'm right, there should be one and the same coupling constant that there should, I call SU5, and therefore they should run equally. Otherwise, what unification am I talking about? Remember that when people tell you about unification of couplings, make sure you ask them, did you check what happens afterwards? Because people make big fuss about that. There are people even that speak, you don't need grand unification, couplings. Imagine that the couplings unify without new states. Then they would continue diverging, so who cares? There would be a funny, amusing accident. Okay, where here there is a genuine phenomenon of. Now this is equal, So I can, okay, I can check this. Okay, so far so good. So what do I get here? So I have to look at this piece plus this. How much is that? This is 33 plus 11 is 44. 44 thirds. Plus things that are equal. 22 thirds. Am I wrong?
$99.
Did you get a 1/4 there? Did you calculate
Sorry?
it? Half plus half.
It's called 1.
Oh,
Half plus half. Assumed it was equal to 1.
oh, sorry.
Back on the envelope, as you said.
It's like
Calculation. Wait a minute, I can't stand it. Okay, we are going to go in a second. Let's try to, let's bear with me. Let's fight this out.
77/6.
No, this should be equal, okay? So the rest was equal, there was no problem, right? This is equal to this, these two are equal, so I have 33 thirds plus 11 thirds. Why did I say this was 11 thirds? The X boson gives me 11 thirds. Every gauge boson should contribute with a third, but this is a triplet, so it has a half, and there are two of them. Oh wait, there is also X star and Y star. They are, remember when we did the fermions, you have to include also, you have to include all the states, left-handed and right-handed fermion, you have to have X and XY gauge boson. Plus a half, plus a half. How much would that be? This would be 2. Plus 6 degrees. Now we go 2. No, you wanted, no, you didn't want 2. So this would be 22 plus 33 would be 55. Well, I'll tell you why I like better 55 in a second. Plus other things. Let's try now. So I should multiply this by 2.
So 11, yes.
Look at this.
11.
This is 33 plus 22. It is 55 thirds. Plus, this was the same.
Yes.
Now notice what 55 thirds is, by the way. This is 11 thirds times 5, because these guys live in the adjoint of SU5, and the adjoint of SU5 has n. See, when I sum all the gauge bosons, I get the adjoint of SU5. A blue ones, I have to get 24 of them. So this is 55 over 3 is 11 over 3 times 5. This is the n of SUN that you and I computed by induction.
Yes.
So we got it right. So see, it's a true unification. The presence of new states, okay, would make sure. But we need unification, okay, and let me just finish the story of grand unification just to tell you where we stand today. The believer in supersymmetry got very excited in the early 80s when the measurements of the coupling indicated, although you don't get unification in the standard picture, you get it in the supersymmetric standard picture. When you add these funny partners, every guy runs differently, but now they would meet. So if you believe in what is popularly called SUSY, low energy supersymmetry, you will get unification scale around 10 to the 16 GeV, which predicts proton lifetime about 10 to the 35 years. So you can still go around screaming, and asking people to go and measure and saying, please go on and keep looking for, this is why many many are asking, including myself, I love grand unification, that a new generation of experiments comes about, and that of course is not easy. You see, Super Kamiokande is 50,000 tons of water, okay? In order to improve it by an order of magnitude, you need a huge enlargement. With the background and everything, you estimate that you need now 1 million tons. Okay, so there is engineering problem, there are all kinds of things, okay? But there could be unification. Supersymmetry people found exciting, I told you today, this morning, because then there is no Higgs problem. In supersymmetry, everybody is equal to everybody else, so Higgs is like Higgsino. Higgsino mass is protected, so you will sort of get another thing. I still find this sort of picture, and I have vested interest actually. In 1981, Marciano and I, we even at that time when the couplings looked differently, we said that we believe in supersymmetry, and we said if this is to work, top quark has to be very heavy, around 200 GeV. So 1901, 10 years before lab, okay, a prediction was made that sin squared W should be 0.23. So you see, the problem was because in order to run this, you needed the value of sin squared delta W. It was more like 0.20 at that time. The thing is still that you don't know neutrino mass and all of that, and the fact that you don't unify fermions, it's not so nice. So I just tell you that there is a theory which is very popular. I'm not going to build it today, of course. It's based on the S group SO10. Anyway, maybe I managed to convince some of you that the world ought to be left-right symmetric. God can be left-handed, but not an invalid. If you believe in left-right symmetry, you cannot go to SU5. That's not big enough. SU5 is just big enough to unify SU2 and SU3, but now I have SU2 cross SU2 cross SU3. And actually it turns out that the theory that does that is SO10. So the thing would come out of SO10, you put all the fermions. How many fermions do you have? 5 plus 10. SO10 predicts another guy. Well, it has a left-right symmetry. This is a left-right symmetric theory. You could show into what is called a 16-dimensional representation. This is a spinor. Or, you know, just like Lorentz group has spinor. Imagine that Lorentz was Euclidean. Then it would be a spinor of SO4. So SO groups also have spinors. Just do one trivial thing. How do you get these spinors? You don't write G mu nu. You just write delta H. Of course, people knew this before Dirac, okay? Mathematicians knew it, okay? This is called the Kronecker algebra. Then you build the generator the same way that Dirac builds the commutator, sorry, anti-commutator. And as in Lorentz group, you introduce gamma 5. I don't know how to call it, which is the product of gamma 1 to whatever. In SO10 would be gamma 10. Right, call it gamma 5, so you have this irreducibility and so on. So in this theory, you unify the family, you predict the existence of right-handed neutrino, you predict neutrino mass and so on and so forth. So if you like neutrino mass physics, then this is a far more beautiful thing. But that's another story. So I think this is the right time to wrap it up. Sorry I took 10 more minutes. But
Is this also a term related to SUSY?
not necessarily, no. Whatever you have, you can make it supersymmetric or not. So each of these, and it has its own challenge when you want to write it in a supersymmetric manner. Now the thing about supersymmetry, that even if you don't like it, that adding this complicated thing, the supersymmetric field theory is very nice. Let them say, it's a pleasure to learn that, whether you believe in it or not. Okay, they are very interesting, very unusual things that happen. that some days when you, no, some days often the infinities of field theory disappear, most of them in supersymmetry. So it's kind of nice. So if you like field theory, then I advise you to try to learn supersymmetry, whether you believe or not. So for many years one studied, more supersymmetric version because supersymmetry became a dogma. Now these days one went back also trying to understand both. It's good to be open-minded.
So is SO10 a good candidate because we also have problems?
I think that I would find this as a far more natural theory than
The quark
SO5.
electron mass problem we had.
The quark electron mass problem that we have, oh, this is an excellent question, okay, I'm glad you asked. So I'll tell you here. You see, you can imagine what would be the SO10, by the way, now that you ask. Okay. The maximal subgroup of SU5 was SU3 times SU2. The maximal subgroup of SO10, one in particular is very interesting, is SO6 times SO4. You agree, obviously, this is a subgroup. SO4 is SU2 plus SU2. Does anybody knows what is SO6? SO6 has how many generators? 15. No.
Yes. 30. 6 times 30.
Why did I say 15?
Yes.
Yes.
Yes, 15.
6
times
times 5
five.
I
Six
know
times
why I
five.
said 15. I was right. Why did I doubt myself? I'm tired. 15. And rank? Do you know the rank of SO6? The rank of SO2 is 1. The rank of SO4 is 2. It's 3 actually. For even SON it's half. Do you know a group with 15 generators and rank 3? You know it actually. 15 generators. It doesn't ring the bell, 15 generators.
SU4?
SU4. SU4 has 15 generators and the same rank. Groups are classified by rank and generators, okay? So it's not surprising that this is the same. It can be shown. So you see what you have here. You have the left-right symmetry. This is SU2L plus SU2R. And this is SU4. This is a beautiful idea of Adi and Salam, according to which the leptons are just the fourth color. This is how it all started. It started here in Trieste. In the summer of, 72, Patti used to come and visit Salam in the summer, and they come up with a picture of quark-lepton unification. The leptons are violet, what should we call it, the fourth color. So in other words, you have U, U, red, yellow, blue. This is the doublet of the standard model, right? D red, D yellow, D blue. This is the doublet. I'm now drawing in the other direction, SU2, color here. In the standard model, these are the doublets. But according to Patti Salam, there is an SU4 color symmetry between these guys. It's automatic in SO10. If you like SO10, you have to buy this picture, okay, it's there automatically. And you understand immediately why the prediction of the SU5 minimal thing, if you don't break Patti Salam, you will always predict the down quark as the same mass as the electron, up quark as the same mass as Dirac mass for neutrino. It's called the Patti Salam symmetry. So the thing of fermion masses, if you take the minimal Higgs, remains the problem. But you have to give right-handed neutrino mass. When you do that, you actually correct. You have to do an additional Higgs. that will correct this relation. So there is something very beautiful. This is 1992 paper by Babu and Mohapatra. I will show that if you correct for the fact that right-hand neutrino must have a mass, right-hand neutrino must get a mass, at the same time you're going to get new Higgs contribution from this new field that will correct the relation between quark and lepton masses. And that's what you like. Whenever you have, when you don't have to build models, whenever your theory does something automatically, and you have to give right-handed neutrino mass in order to get the right mass for the neutrinos, okay, right? We studied this, the seesaw mechanism and so on. Okay, then it turns out this is correct.
Also from the electron, it corrects the problem.
Right, it's the minimal SO10 theory is really beautiful. It has some non-trivial group theory behind it. It's not that simple. There are more fields and more group theory to study, but also that is a fun for any of you that may be interested. The thing to study is SO10. It's far more lively, far more interesting than SU5. It's too easy, too simple SU5. There's almost nothing to learn. And this is, I would call it the first really grand unified theory, because it's not enough to unify just interactions. I want to unify matter also. We wanted to call it unified. Okay, so at this point, now we stop and oops.